Okay, we're going to talk about using inductive reasoning today. Inductive reasoning is making a guess and checking it. And so all of these examples and things are going to lead up to us kind of finally talking about using inductive reasoning to find patterns and to verify conjectures. So if we look at these 4 patterns here, you can probably do these on your own, but I'm going to step through the process of making these conjectures, okay? We look at Monday, Wednesday, Friday. We notice that Tuesday and Thursday are missing. And so if we're going about the pattern of skipping a day, we're going to go on to Sunday as our next term in the sequence. Okay, so Sunday is our next term. If we look at what's going on here, we're going 3, 6, 9, 12, 15. So we're going to be adding 3. So 18 is going to be our next term. In C, we're going left, right, left. So our next term would be right. And if we look at the number of zeros behind the decimal point, we have 0 zeros, 1 0, 2 zeros, 3 zeros. So our next logical one is going to be to put 4 zeros behind there and keep our 4 as is. Okay, and so we're recognizing patterns here. And as we go on, we're going to talk about vocabulary. Inductive reasoning is the process of reasoning that a rule or statement is true because specific cases are true. Okay, so this rule is really talking about a pattern or a sequence. Okay? A pattern or sequence. That's the rule that we're talking about. So when we talk about patterns and sequences, inductive reasoning is going to help us make guesses. Now, our conjecture, this is going to be our guess as to what comes next, or our guess for what happens. Okay? And as we unfold this next couple of slides, you're going to see how making a conjecture can help us find patterns and verify what's going on. Okay, so if you need to pause and take down these notes, go ahead and do that. We're going to go on. So we're going to complete each conjecture, remembering, of course, that this is guess. Okay. The product of an even number and an odd number. We are guessing at what this means. And by guess, it's not so much as a guess as it is an educated guess. Okay? So the product of an even number and an odd number is blank. Well, we don't know. So what we're going to do is we're going to look at specific cases. Like 2 times 3 is equal to 6. 2 times 5 is equal to 10. 3 times 4 is equal to 12. Look at what's happening here. If we have an even number and an odd number, we're ending up with all even numbers. So my guess is going to be that this is even. That's my conjecture. Okay? Now, if I look at the number of segments formed by n collinear points. Okay, so what I'm going to do is I'm going to say a segment has at least 2 collinear points. Okay, so these 2 points are collinear. Okay, so if I have 2 points, I have 1 segment. What if I added a 3rd point in the middle here? Well, I would have 1, 2, 3 segments. So if I have 3 points, I have 2 plus 1, 3 segments. What if I had 4 points? So I'll erase this, and I'll put my points down. 1, 2, 3, 4. Now watch what I do. I have 1. I have 2. I have 3. I have 4. I have 5. I have 6 distinct segments here. Okay? So when I go to put on 4 points, I've got 3 plus 2 plus 1 equals 6 segments. Let's make a guess. So if I look at 2, I have 1. If I have 3, I have 2 plus 1. If I have 4, I have 3 plus 2 plus 1. So my guess is going to be that if I have 5, I'm going to have 4 plus 3 plus 2 plus 1 segments, which gives me 10. Okay? And so the number of segments formed by n collinear points is the sum of all whole numbers less than n. Okay? Because as you can see, I have non-overlapping segments that are formed by these pieces. Okay? And so these conjectures allow us to make guesses. So if I say the product of an odd number and an even number, I'm really repeating what I said before. Okay? And so when we're doing these conjectures, it's really just guessing at this. So I'm going to go ahead and change this to odd because I already did the other one. Okay, so an odd number and an odd number is blank. Well, if I say 3 times 3 equals 9, 5 times 5 equals 25, 3 times 5 is equal to 15. Notice, odd, odd, odd. So I'm going to say odd here. Okay, so I'm making these conjectures based on what I know and trying to figure these things out. Okay, when we're verifying conjectures, verifying means we're saying if they're true or not. We're talking about counterexamples, and this is what we do naturally as human beings. We're trying to find a way to say that someone is wrong. So if someone tells us that we never clean up our dishes after we have dinner, well, we're going to try to find a counterexample. We're going to say, no, I did last night. I cleaned up my dishes after dinner. Okay? So that's where the statement is not true. And so if I say that the sun never shines, a counterexample you might say is, it was sunny today. Okay? So I might say it was sunny today. Or I could say the sun shines daily. Okay? And so a counterexample is really just trying to prove something false. And so this is something that we're naturally really pretty good at. Okay? And so how does this fit into inductive reasoning? Well, first we're going to look for a pattern, which we already talked about. Okay? Then we're going to make our guess, our conjecture, remember? And then we have two choices. One, we prove it true. Or two, find a counterexample. Okay? This is the process of inductive reasoning. This is what we as humans do. Okay? And so when we're doing this, here's what we're going to do. We're going to try to practice finding counterexamples. Okay? So for all positive numbers n, 1 divided by n is less than n. So let's look. What if n was equal to 1? It would follow that 1 divided by n would equal 1 over 1. Should be 1. So 1 over 1 is equal to 1, so it's true. But what if n was equal to 1/2? Then we would have 1 over n is equal to 1 over 1/2, which would be equal to 1 times 2 over 1, because we divide by a fraction, we multiply that reciprocal, is equal to 2. Okay? So n equals 1/2 is greater than, sorry, let me write this correctly. If n is equal to 1/2, then that means that n would be greater than, sorry, I messed it up again. N would be less than 1 over n. So this would be a counterexample, okay? The next example. For any 3 points in a plane, there are 3 different lines that contain 2 of the points. So let's look at this. If I have 3 points in a plane, I can draw 1. I can draw 2. I can draw 3 lines that contain those 2 points. But a counterexample could be this. What if those 3 points were collinear? Then I would only have 1 line that went through the points. Okay? What about for any real number x, x squared is greater than x. So let's greater than or equal to. So let's say x is equal to 2. Then it follows that x squared is equal to 4. So x squared is greater than x. But what about if x was negative 1? Then it would follow that x squared was equal to 1. So x squared would be greater than x. But what if x was equal to 1/2? then it would follow that x squared was equal to 1/4. So x squared would be less than x. That is a counterexample because we are trying to say that it is always greater than, but in this case it's less than. What about supplementary angles are adjacent? Adjacent meaning 3 rays form 2 angles. They share a common side. So that would be like this. I would say this is 10 and this is, I don't know, 80. So these are next to each other. They're adjacent. Okay, so we're talking about supplementary angles are adjacent. Well, if I have 2 supplementary angles, let's say 130, and I can draw this, and over here I've got a 50-degree angle, they don't necessarily have to be adjacent. These two aren't even connected. Okay, so those 2 angles are supplementary, but they are not adjacent. They don't share a common side. Okay, and so all I'm doing here is disproving each of these things. Okay, that's how we're working with this right now. Okay, and so when you're doing your homework or when you're studying conjectures and studying counterexamples and inductive reasoning, it's a process that we already know how to do. You're trying to prove something false that someone is saying. Okay, thanks for watching.